Great. Hello. Can see a few of you are out there, so thanks as always for being here for the live stream when you can make it. It's just helpful to have a little bit of interaction at least when I can get it, so thank you for that. If you're watching the lecture later, I hope you've had a good week. Happy Monday, Edcast. Nice to see you as always. Okay, we're starting week 7. Happy Monday, Magenta. Nice to see you as well. So I am... just before I came on, I thought I should not have put that line 8 on the agenda, but I did. So whatever that means for the rest of my day, that will be what I will intend to do, which is get your project ones scored and back to you today. So doesn't do me any good to sit on them for any length of time anyway, but whatever that means for the rest of my day, I do intend to do that. So hopefully you'll see your Project 1 scores back sometime today. And hopefully your experience was okay with it. Hopefully you were able to identify areas where you could use some practice. If you just kind of breeze through it, then all is great. If you found things that you know could use some improvement in terms of your understanding or your technique, well, that's a good thing too, because that's why we are here. Yeah, I guess that's most of what I had to say about it. It is a thing that takes practice. Not everyone loves programming as much as other people, but we all kind of respect the craft of it because it is the tool that we need to express our ideas in computer science. So whether or not it's your first love and you feel as passionate as some people about the actual work of writing code, you need to be good at this craft to be in computer science. You need to be good with the terminology. You need to be able to look at code and understand what it's doing. You need to be able to craft algorithms. And to do that, you need to know what is possible in a computer program and what isn't. I'm saying all of that because if you are sitting back and waiting for my labs and my projects to get you to practice and you need more practice, then that's probably not enough. You need to go find other ways to practice your craft. What I do is I use assignments from my classes. So when I pick up a new language, I will often go back and just implement labs and or projects from my first semester class. It's not difficult to pick up a new language in most cases, unless the language is designed for a completely different style of programming. But if you are doing C, C++, Go, Java, JavaScript, Python, PHP, basically the 1,000 most popular languages are all written to do the same style of programming. And their syntaxes are going to be close enough where it is not difficult to pick it up with some practice. Good morning, AP Fierro. Nice to see you here. So anyway, some of us, myself included, need more practice than others do, but we all need it. So if you feel like you are struggling with a particular area, then practice it. And that probably means that you need to do work beyond what it is I have to offer for assignments. So just a heads up about that. I am presently about to start learning the Odin language, which means that I'm going to have to practice it to get its syntax down. It's very C-like, so I'm not super worried about it, but I do need practice. Okay, so Tony, nice to see you. I'll try to remember Tony from the tag I can see. All right, so Magenta's got a question on Project 1. Yes, so the syntax for calling member data or member functions for classes and structs in C++ is exactly the same. And you'll recall that the only difference between a class and a struct in C++, the only difference is that the default access is public for a struct, private for a class. And the default access can be overridden with access modifiers. So they are literally at a point exactly the same thing. All other syntax is the same. The way they function beyond the default access is all exactly the same. So that's a good question. It does take some getting used to. like when is a struct a better choice than a class? And the answer is technically there is never a better time to use a struct over a class or vice versa. With some experience, you'll start to make those choices for yourself for particular reasons. So for me, as an example, if I just need to bundle up some variables and I'm not worried about attaching fancy algorithms to that data or anything, then I use a struct. If I need to bundle up some variables and also connect some fancy algorithms to them, then I'm going to use a class. It's a good question, though. Okay. So practice if you need it. If you need a place to go find practice, your first semester programming class had labs and projects, and that's what I do. And I find that useful because they usually kind of build up from the basics to where we're getting into some real programming problems. So I find those useful. Okay, so project 1, barring some incident in the world, I should get those back to you sometime before, well, I wake up in the morning, but hopefully before I go to bed tonight, like at a reasonable hour. Let me open up the... So we just got through with project 1. Project 2 is October 30th. So that means it's 4 weeks from now, which means that you have 4 weeks to work on at least parts of it over time. And don't forget that the first project was a 6-week project. And the only requirement that wasn't basic programming was that it include a struct or a class. We got structs in week 4, classes in week 5. But the entire project could have been written in week 1 with your PNA 1 skills and then refactored to place a struct in there. If you've never done that before, then it's a good thing to practice. Like, can I implement some or part of this project, even if that means that at some point later I have to go back and refactor it, which is the term we use for reworking code to be better. Can I start project 2 today as an example, and then at least some part of it, and then kind of over time refactor it? I may or may not be able to, but let's go peek real quick now that we're talking about it. So we're going to be reading a CSV file. That means that I can do something today because I know how to read a file and I know how to parse it. So I can actually begin work on that, and I know how to parse the contents of a file with data fields into a struct instance. So you can actually begin that process today if you were so inclined. Doesn't mean you have to. Obviously, I can't control your scheduling of your work, but I'm just pointing out to you that October 30th isn't the day when you start project 2, and then you email me at 11:59 and say I didn't have time to finish it. And then I will say, well, what about the 6 weeks leading up to that point? There's 4 weeks between now and October 30th. So sooner than later is the time to start it. You know how to load a file. You know how to parse a file. You know how to parse the data fields into a struct. You can do all those things today. And at the end of today, there is a very good chance that you can actually populate a vector with instances of a struct, which then gives you ability to do things like loop through the vector, sort the vector, things like that. So anyway, heads ups about that. It's actually a 4-week project. All right, we are in week 7, so let's go look through it before we do code stuff. We're finally getting to the point where we're not just doing basic syntax, so that's nice. It's hopefully you'll find it more interesting as well, because this will be the first time when we've done any actual algorithms this week. Up to this point, we've really only been doing just some basic syntax practice. So the stars of the show this week are the standard string and the standard vector. You're going to find that they share a lot of things in common, string and vector. And knowing that they share a lot in common in C++ means that the same approaches, the same approaches to processing a string in C++ will work for vectors. So that's super, super handy. I don't know if you guys have noticed it, but Canvas changed this little icon here. And it just messes with me because now every page that used to have the other icon looks like it's not formatted correctly, but they added this clunky icon in here that's got space around it apparently. Anyway, onwards and upwards always in the world of Canvas. Okay, so the lab, let me pop it open. So this week we will be back to a unit tested lab. Oh, by the way, I already got through last week's labs, and one of the reasons I was able to get through last week's lab so quickly is that you all did such a good job on them. So thank you for that. That let me complete all the grading of your labs from last week so that I could focus this afternoon and evening and night on your projects. So that's great. See, there's that stupid icon. And you can see the spacing around it. Discussion this week. So discussion this week is asking you, we've done this kind of thing before, is to use your own words to describe what a vector is and what it does and what you can do with it. And I think it's important to know that you can and should do that, because your explanation in your head of something that is how you understand it, if it's different from mine or anybody else's, doesn't make it wrong. It just makes it different. So I want you to sort of develop the confidence that if you understand a thing and you have words that you use to describe the thing that you understand, it doesn't matter if your words match everybody else's words. As long as, so if we sort of have a chance to see how we all would describe this thing for ourselves, then, you know, in there also may be the language that some of us need to better understand what a vector is. And what's last? Yeah, so lab and discussion as always, and then it's time sooner than later to start that individual project. It's not hard, it's somewhat repetitive actually, but you want to give yourself lots of time. Like if you can just in the first week put to rest the whole file part, reading and parsing part of that project, that eliminates that obstacle for doing the rest of the project. And that is the main technique that you have already practiced with, and you'll get more practice with that in the lab this week as well. Yeah, so Magenta likes the old downloads in a separate thing icon. I do as well because it doesn't screw up the formatting. So it just really irritates me that they introduced this icon that screws up the formatting because they put spacing around it. And maybe they thought that's a good thing. I suspect, like so many things in Canvas, that some person on some team way out there on some branch of the system made this change, and it shows everywhere and no one ever discussed it. Okay, so I think that's all I have to do with that stuff. And it's just that. Anyway, yeah, every time they make a change in Canvas, unless it's to fix something that's broken, which they never do, by the way. They never fix things that are broken. They just add new things that break old things. So what are you going to do? Okay, so let's switch over and do some code stuff. And I'm going to kind of build up a picture, at least I hope. My intention is to build up a picture for you of how, so the last item says function composition on line 21 in my agenda. But the idea here is that what you want to learn to do is kind of see how you can develop algorithms on top of other algorithms, which are on top of other algorithms. So you want to be able to compose functions by building their solutions on top of other functions which already exist. And I'll just sort of give you a spoiler about this. So the spoiler is, if you have a vector, which is like a dynamic array, so it's a collection of things. If you were to have a collection or a vector of strings, and then you were to loop through the vector of strings, you could perform string algorithms on the individual members of the vector. That's what I mean by function composition. Oh, I have a collection of these things. If I loop through the collection, I can actually apply operations to the individual elements of the collection, the string. It also turns out, by the way, that if strings are actually themselves collections of characters, which they are, then I can loop through a string and perform character operations on the individual elements of a string. And I can compose all three of those layers into a single algorithm. So I can take a vector of strings and loop it to get the individual strings. I can take each individual string and loop it to get the individual character. And now I can apply operations to that individual character. There's not really any lower you can go in that composition than the character itself. So once you got down to the level of the character, that's kind of where the rubber meets the road. So I hope that you'll walk away this week with a sense of how we are composing functions in this way. We're going to have a vector of strings, and we're going to then cause string algorithms to operate on each individual item of the vector. And as a part of those string operations, we will be applying individual character operations to the characters in the string. So that's what I mean by composition. Let me fire up a REPL for experimenting with 21 week 7. Okay, so I'm actually going to start with characters because it occurred to me just before I started talking at you that a lot of you may not know truly what a character is in C++, like what actually is going on with the character. So let's make one. In fact, let's make a couple. So, no, let's just make one. Character C1, which I will make a little a. So I'm going to use the big namespace directive so I don't have to waste space on that. So if I were to see out that. So everyone, I think, knows what to expect here, right? So a character is just a single character in C++ and is marked by single quotes. Most of you at this point know this, but it's probably a good reminder. That's all a character is. It's a thing in quotes. Strictly speaking, by the way, it is an ASCII character. And that's useful to know because that tells us another piece of information that we can use. And I'm going to just cheat real quick and show you an example in code. A thing. So this is kind of weird. Because it allowed me to add 1 to the character A, but then it printed out the number 98. So what is going on here? And what's going on is ASCII characters. So let me see if it might actually be in here. If I type man ASCII, darn, okay, it's not. We'll have to go out to the internet and get it. That's okay. So when we say ASCII, which is what this is how C++ represents characters. The Go language, for many of you, you had Go last semester. The Go language does not use ASCII to represent characters. It uses UTF-8, maybe UTF-16. Anyway, what ASCII means is it is a way to encode characters as integers. That's all it means. In the computer, in C++, when you declare a character, it's really just a visual representation of an underlying code. So ASCII means integer codes for characters. That's all it means. But because they're codes and they're integers, you can do math on them. So you can do things like, well, what does it mean to add 1 to this character, this ASCII character C1, and C++ spits out a 98. What that should mean, by the way, is that the ASCII code for little a is 97. Let's see if we can find a table in here. If not in here, we will. Okay, so here is a table. We'll use this column that says this is the decimals for stuff. So let's go to 97 and see what it is. So here's 97, and it is in fact a little a. 98 should be a little b, except for when I do direct math on it, it looks like an integer again. There's a really weird way of making that look like a character. The appropriate way, anyway, to do it is with this funky looking casting operation in C++. The Go language, for those of you who had it, the Go language makes this casting, this conversion very simple, but in C++ it's more complex. So this is how I convert something that's not presently being interpreted as a character into a character. So what it should mean is that instead of seeing the 98, I see the little b. All right, so now I see the little b. I just wanted to stop on the character type in C++ to let you know that a lot of these operations are actually kind of, they're built on the idea that there's an integer code under there. I don't think it often affects us in this class at all to know, but just so you know. Characters, the char type in C++ is an ASCII char, which is an integer code system. Okay, so now let's do something more interesting with the chars. Let me move this over here, which is to run tests on them. So I'm at C++.com. If we go look at CC type, so CC type at C++.com, so the URL is C++.com. The search I'm doing is CC type. What? I don't want to log in. Okay, CC type, character handling functions. So why are we starting here? Because we are building up to this idea of composing algorithms by using functions on top of functions, kind of. So character handling functions. These are all of them. This first table is a bunch of tests. So we can test to see if a character is alnum, is alpha, is blank, is control. All the way down is X digit. So a whole bunch of tests that we can use to see what a character is, at least as a category. And then we also have two converting functions, a function to convert characters to lowercase and one that will convert a character to uppercase. So let's just click on one. So check if a character is alphanumeric. You'll notice that the parameter is an integer, by the way. The reason why is because it's ASCII text. So an ASCII character is an integer code, has an integer code. So a function that is written to accept this integer code works just fine. So one of the weirdnesses here, and we'll see if it still works this way, is it returns integer. So let's see what the effect of that is in our code. So we can pass a character in, knowing that a character has an underlying ASCII code, and then we're going to get an integer back. But what does that mean? In terms of the return value. So it says a value that's non-zero if true, and a value that's 0 if false. So let me just show you as a heads up one of the possible problems here. So let's just do a test on C1. So if is alnum C1. So a lot of us are going to want to say equals true. We should, by the way, let's include CC type. even though I think we get it for free. C1 is alphanumeric. C1 is not alphanumeric. Alphanumeric simply means a letter of the alphabet or a digit. So let's, and a lot of us are going to want to write this. Now C1, which is the letter A, is alphanumeric, so it should be true, but let's run it just to see what happens. All right, so it says false. Now, why does it say false? The reason why it's coming back false is because this is a Boolean comparison, but the function returns an int. So that's potentially a pain in our rear unless we understand how to simplify our code to deal with this problem. So one thing we could do is we could say if is alnum not equal to 0, that's what the documentation says. All right, so that works, but that's kind of awkward also, because the not equal to 0 doesn't speak to me, at least, about what's going on, because I know this is kind of a true-false test. So the way I would simplify this is simply say if is alnum. In C++, if you say if is alnum without comparing it to 0 or true or false, what C++ does with this is basically look for any truthy situation, and that's the word we would use, is truthy. So what would be truthy about is alnum? It's either literally true, Boolean value, or it is non-zero, which would be another truthy situation. So it reads a lot better this way too. So if we use its truthiness and we say if is alnum C1, there's nothing confusing about that. If it's alphanumeric C1, then we do something. So this is how I recommend you write these. If you write them as Booleans, they won't work. You can write them with integers and they will work, but it makes the code harder to read, in my opinion. So we will write these character tests this way. And it should say it is alphanumeric. So let's change it. We'll make it a punctuation mark, which is not alphanumeric, and run the program. So that's not alphanumeric. We could change this test. I'll just show you real quick some of our options here. So we have an is punctuation one, is printable character, is upper, is lower, is digit specifically, is blank. There's an is space to look specifically for the space character. There's all these tests. So let's try is punct, which an exclamation point should be true. Oh, wait. Is punctuation is not. Well, I don't want to lose the code from the examples. Is not punctuation. Okay, so that is punctuation. So these character testing and converting functions, let's go check real quick, by the way. So what do the converting functions take? Take an int, return an int. Fortunately, when the data type is a character, the transition between character and integer is quite fluid, and I'll just prove that real quick. So let's find one that would be fun to print. Let's find the tilde. Where's the tilde? I know I could control F this and find the tilde real quick. There's the tilde. Interesting. That's character 176. Okay, so let's try the tilde just for fun. Char C2. The tilde is 176, so I'm going to initialize it as a number, and then I'm going to print it out and see what it looks like. It printed as a non-printable character. That's a bummer. Let's try the little a again, which is a 97. Okay, so I guess I got into kind of bad. I guess because of these different possibilities for the tilde, I didn't get what I wanted. I can live with it. Okay, so anyway, I initialized it with an integer. And I just wanted to point out to you, and we could do the same thing. So I can say C2 equals to upper C2. So I'm going to overwrite it with its uppercase form of itself, and it should now be a capital A. So now it's a capital A, just to kind of show you the integers and characters are interchangeable. But this kind of Boolean truthy situation is not interchangeable. So just be on the lookout for the test functions. But the converter functions are happy to kind of go integer and char back and forth. Okay, so that's a building block. We can do these various things with characters. We can test them to see what category they fit into. And we can also convert at least the alphabetical characters from upper to lowercase. Let me get rid of this thing and build a new one. Okay, so now let's go one level up from that. So strings. And let's go to C++.com and bring up standard string and see what it does. Sequences of characters. So that's important. A string object in C++ is really just a collection of characters with a convenient syntax for representing them. The convenient syntax is the double quotes. The double quotes allows you to represent a sequence of characters without having to create an array or a vector to hold the separate characters. So that's actually just a syntactical gift that we can represent a collection of characters with double quotes, even though functionally it is a collection of characters. Lots of scary stuff. Constructors. And we've already seen, by the way, let's just look. We've used the default constructor, which is number 1, which constructs an empty string with a link 0 characters. We've also used this constructor, number 2, which constructs a copy of the given character. And then there's several other options for creating. We've probably used this one on occasion as well, number 4. Anyway, so we've constructed strings. You can construct them empty, or you can construct them to make copies of a specified string. So that's the constructors. We know that we can assign strings. So we can say, for example, I'll switch over. Let me make one, string S1, default constructor, empty string. Let's capitalize it. Hello. 10 times. So we just read that. We can also do this. We can also say using the assignment operator. So that was all in that one page of documentation that we can construct with the default constructor. We can construct with an overloaded constructor, and there were several others. We also have access to the assignment operator, so we can assign strings to each other. All right, so what else can we do with the string? Iterators. We are going to talk about the concept of an iterator, but we're not going to use these iterator functions. We are going to take advantage of the fact that strings can be iterated. An iterator is simply something, you can think of it as an invisible marker that walks across a collection. If you've ever written a for loop to process an array, then you have done a form of iteration. But that strings have iterator functionality built into them is highly useful for what we're going to do here in not too long from now. So we're not going to use these iterator functions, but we are going to note that the string has iterator functions. Very useful to know. We are going to use some of these. So strings have a size function that tells us their length. They also have a length function that tells us their length. They're the same thing. These are just here for some compatibility issues and for some people who maybe are used to the function name size versus the function name length. So when you see functions that seem to be duplicating themselves, it's usually some kind of maintaining compatibility between things kind of effort. We're never going to worry about max size, but strings do have a maximum amount of characters they can hold. We're not going to resize them. We're not going to worry about capacity reserve. Clearing is handy. It's a way to empty the contents of a string. You can also assign empty string to a string and clear it. Empty, which is a test to see if a string is empty. So we have that. We also have these two functions, the square brackets operator, so that we can address the characters in the string as if it were an indexable array. We also have the at function, which does the same thing. Now let's go look at. So the at function, if you give it a position, gives you a character. So the at function is the same as the square brackets in the sense that it returns to you the character at a given position. So if you put a position inside the square brackets, you get the character at that position. If you put a character as the parameter to the at function, you get the character at that position. These are 0 indexed, and if you come from Go, that's the same thing. Most high-level languages are 0 indexed when it comes to collections. Only odd languages like Lua don't do 0 indexing. Maybe Basic. And then you can also get the back, which is the last character, or the front, which is the first character of a string. Let's go, we'll play with some of those in just a bit. What else can we do with strings? We can use the plus equals operator to append something to a string, so grow it. We can also just use the append function with a parameter to grow a string. We can use the pushback function to append just a single character to a string. We can insert stuff into the middle of a string. We can erase stuff from various locations in the string. We can replace things in the string. So there's a lot of stuff that we can do with strings. What else is there that we might use in this class? Possibly the find function, which is what it sounds like. Look for a string inside of another string. This is kind of like look for a needle in a haystack. Find one string in another string. And then substring may or may not be handy, where we grab just a part, a subset of a larger string, which we call a substring. So that was just a very quick review. There's also, let's see, the plus operator to concatenate strings, but it doesn't come with the freebie assign it back over the top. Relational operators, meaning greater than, less than, greater than, equal to, not equal to, equal to, so you can compare strings character by character. And then we have insertion and extraction operators, which we're not going to use. So that's a lot of stuff. You don't need to memorize it. You do need to know how to find it. So if you come to c++.com, oh wait, this is ask. No, it's not. Yeah, that's it. If you come to c++.com and you search for standard string and you click on that, then you will get the page that documents all of the functionality of the C++ string. So why is that handy? Well, because we can do things, got to watch the time. We can do things like S1 has characters, right? We could also have used the length operator for that. We can also do things like this. Of S1 is remember that front function? Last character of S1 is S1.back. We can get targeted. Characters. Same thing. That's all. So let's just see if all that works before we get too far. So notice I'm using the S1 string object. I should have used S2. Yeah, I'm going to use S2 instead. Because S1 doesn't have any characters, so it'd be kind of a bummer to do this with. Okay, so 10 characters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is correct. First character is the big H, yes. That was from the front function. The last character is an exclamation point. That's from the back function. I can use the square brackets to index the string at position 0, which gives me the big H. I can use the at function in the exact same way. But the advantage of at and the square brackets operator is that I can move it around, right? The front function can't move around. The front is the front is the front. But I can move around with these two and get characters at different positions. So that's the E. So that's a lot of just sort of how do I don't know if you noticed, you probably did, by the way. I am specifically interested in the functions that get me individual characters of the string. And that's because we were just talking about doing things with characters. Well, if I can use the string to get its individual characters, then I can apply those character functions to them. So let's add something so that we can now do that. Let me have a quick peek and make sure I did I mean to do any more of these? Clear, empty, at, front, back, front, appending. No, that's all the ones I meant. Okay. So we looked at characters and how we can test them individually. We can convert them individually. Now we're beginning to look at strings as collections of characters. And it turns out that strings have functions that let us get at characters in various positions. The reason we would do that is because we want to do things like change characters. So let's change character 0 to a J, to show that we can use these operators to access and overwrite individual characters if we want. So notice there's Jello because I went into the 0th character and I overrode it with a character. You can also do that. So let's see, the O is 0, 1, 2, 3, 4. Let's change character 4. So s2 dot at 4, same thing, just a different look for the same operation, equals a y. So those functions are interchangeable. You use which one you like the looks of better. I'm in the habit of using the square brackets, although I've been trying to get out of that habit. I don't know why, other than I guess just so my code looks more consistent, that I'm using functions where functions are available. But I'm still not consistent about that, I don't think. Okay, so I have overwritten individual characters. I can also do tests on individual characters. So if is punct s2 dot back punctuation, which I expect it to be. So notice here I'm going to pass in. So now I am sort of doing some composition of functions. So I'm going to use S2, get the back character, which is the last character. I'm going to pass that to the isPunct function, and then I'm going to test all of that in a truthy if statement. And it is punctuation, which is correct because it's an exclamation point. So now I'm starting to do a little bit of composition of functions. Okay, so now let's make this a lot more entertaining or powerful. So it's not unusual that you might want to go through and process an entire string all at one time. So let's say, for example, that I want to make S3 be all uppercase. So when I know that I have a collection that I want to process the individual parts of, the collection is the string S3, the parts are the individual characters, I can loop it. So let's do the old school for loop, for. It's better, by the way, to use size t instead of integer. It doesn't matter a whole lot. Size t in C++ is, you'll see it often used for the indexes of things, and what it's kind of talking about is something that can't be negative. So if I'm going to iterate over a collection, well, there's no position in the collection that can be negative. So a size t iterator is a common choice in C++. It just means always positive, and it also means this is related to the size of something that will always be positive, if that makes any sense. So anyway, this is just to sort of get you in habits so that you'll recognize other people's C++ code. So, but you can also, it's really effectively no different from an integer. It's just a good habit to be in for this kind of thing. If in doubt, use an integer. Okay, I is less than the size or the length. So I want to iterate across the entire length of S3, moving my indexing variable one at a time. So if you've done P&A1 in Go, you've done this before. You did it without the parentheses. Is all. Same kind of loop that you've written, hopefully many of in Programming Algorithms 1. Just a little bit of extra syntax is all. So start at 0. Go one at a time. So 0. 0 plus plus is 1. 1 plus plus is 2. 2 plus plus is 3. Stop short of the size. And it's the less than that makes us stop short of the size. Why? Because we start at 0, which means that we don't go all the way to the size. So the size of good day, good night, is G is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 6, 27. But if I look at indexing, which has to start from 0, G is index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So the length is 27, but the indexing only goes to 26. So the reason why we stop short of the size is because the indexing has to stop one short of the actual size. Size is 27, indexes stop at 26. All right, so why am I doing this? Because I can change S3 at each of those I positions to their uppercase forms, and I will compose by saying that same character at I. So I'm going to grab the character at position 0, position 1, position 2, position 3, all the way up to position 26, one at a time. I'm going to uppercase it, and then I'm going to overwrite that same position with the uppercase form of itself. So I'm going to get the G, uppercase it, and write it back into its same position, which stays as an uppercase G. But then the O becomes uppercase and is overwritten with the uppercase O, and so on. So at the end of that, S3 is going to be all uppercase. So there it is, good day and good night. Notice that it didn't change. If it was already uppercase, it left it alone. If it's punctuation, it leaves it alone. It's just the alphabetic characters that do that. So there is me processing all the characters in S3 by looping S3, processing the characters. So if you look on the agenda, you will see that I have written under standard string for looping. So this is for looping. But C++ has a for each style loop, which you've probably written something that read like this. In the Go language, if you had P&A1 in the Go language. If you've had Python, then you've done comprehensions, which is kind of the same kind of thing. So this is for looping a string. This is going to be for each looping a string. So this is a shorthand syntax. And it has two forms, which sounds intimidating. But some people look at for looping a string and think that that's kind of a mess, and it takes people a long time to get comfortable with the traditional style of for loop. So C++ now has a different way of doing this same problem. We can actually go through a string. This time let's do some punctuation testing. So for so this is a for each style loop in C++. So what we're saying is for each character, which I will label C, from S3. So it's going to go through each character one at a time, and each pass of the loop is going to give me one character of the string from the beginning to the end, and I will have access to that character as the letter C. So let's just print out things. One line at a time. So for each individual character, which I will label C, as I process or loop through or iterate over S3, I'm going to print out that individual character. So each pass is one of the characters, starting at the beginning, running at the end. So each individual character should print on its own line That'll be the thing at the bottom of this program. So here is the for each loop. Gets the G first, which it calls C. That's just a label for this pass of the loop. So the first C is a G, right? And then the second pass of the loop is going to relabel, is going to get the O and label that C, and then I do it. So that is a very clean kind of loop if you understand what it means. So for each individual character, I'll go ahead and label it C, that I get from iterating over S3, do something with each of those individual characters, one character at a time. So there's the C. Let's take the end line off and do a little test with it. So if is punct C, punct, I'll just put a little label on the end, else my punct. We'll start with that. So I'm going to use the same for each loop. I'm going to print out the character, and then I'm going to use an isPunct test on that same character and then print out a message accordingly. And we will see if it is correct. So G is not punct, that's true. D space is not punct. There's a punctuation symbol, the comma, and then I get 3 more at the end with the dot, dot, dot. And we can add more tests in here. So let's add more tests. Else if is space that character. Oh, sorry. Space between else and if. If you're taking assembly, then you know why I did that. Okay, so for now I'm just saying I don't know what the category is because I haven't tested for them, but the spaces are being identified correctly as spaces. Okay, so there is a for each looping a string. So that I can do the individual characters. This is a read-only, by the way, for each looping of a string. Let's do a read-write. And what do we want to do? I'll change, I'm going to take all the, maybe I'll replace all the, vowels. Couldn't come up with the word vowel. I'll replace all the vowels with like an asterisk or something. Okay, so now we're going to do a read-write for each, and note the difference. So the ampersand is the whole trick. That means that this is grabbing reference, which means that I can use this C to overwrite things if I want to now. If you take the ampersand out, it's a read-only, which is good for testing. It's not good if you want to change, because you won't be allowed to change. So let's change. So we will say if it's an A, or it's an E, or it's an I, or it's an O, or it is a U. I'm not going to do the Y's. So if that character C is any one of those things, then I am going to overwrite it. with an asterisk. Let's put a tilde, since I was frustrated with the tilde before. Okay, so that ampersand makes the whole difference. It changes the for each loop from a read-only loop to a read-write loop, which means that assignments to these characters overwrite the original character because it's a reference to the original item. And then you can see at the bottom where I have replaced all the vowels with tildes instead. Okay, so another example of kind of, this one is not nearly as interesting, but kind of taking advantage of the fact that strings are a collection of characters, which means that I can loop the collection and work on the characters. I can test them, I can change them. So that is strings, and don't forget that there are a lot of functions built in. I'm going to leave this actually just so you can see this next bit. How am I on time? I'm doing okay on time. So let's change our search now and go find vectors. Okay, so vector. Vectors are sequence containers. So strings are sequences, but specifically of characters. Vectors are sequences of whatever you want them to be sequences of. So where does it say that it is anything that you want it to be? I guess the easiest way to find it is right here where it says that you have to specify the type of the elements. So a vector is a very flexible collection because it can be a collection of anything. It can be a collection of integers, characters, booleans, strings, doubles. It can be collections of other vectors if you want to kind of spill out into a second dimension. It can be a collection of struct if you want it to be. So a vector can be created to be a collection of anything that you want it to be. Here's what it would look like in code. So let me get rid of this thing for the time being. Bring vector in, and then start up a new main. Okay, so there's a question in chat. I didn't need to, so you didn't need to test for lowercase vowels. It automatically tested for both upper and lower. No, so that's a good question, Magenta. On my code, I cheated. So Magenta's asking about this section of code. What if they had been lowercase? So if the characters had been uppercase, I would have had a problem. I mean, lowercase, I would have had a problem. So yeah, technically I would need, if I didn't already know, so because I had already converted the whole string to uppercase, I knew I could get away with this, but technically you would need to do something like this. And test for both. Now I didn't because I had already converted all the characters to uppercase, so I knew that that was true. But there's also a better way to do that. So let's put that here, put this back, and then comment this thing out. So there's a better way to do this situation where I need to do a test. The better way to do this situation would be to say, is to make a copy of C and force it to be uppercase for the purposes of this comparison. So that would have been the better way to do it, is ensure a case insensitive comparison by giving myself a temporary variable that's an uppercase form of that C and then running the test off that way. Yeah. But I knew I was going to get away with it because I had already done the to upper part with my for loop. So yeah, so Tony asks, you can have vectors of vectors, and you can. I'll show you what they look like. They're nasty, but I have used them. And in fact, in this class, I think we will use one late in the semester. Okay, so how do you make a vector? You make a vector like this. So you have to specify the type. So this will be a type. So let's make a vector of, well, we're going to make one of string. So call it words. So words is a vector of strings. So one vector can only hold one kind of thing. So this vector words can only hold strings in it, but you can make vectors of a variety of different types. Flags, initials, and so on. So you can make a vector of kind of any type that you'd like. And you can, in fact, make a vector of a vector. Usually we'll space this out of something. So yeah, we can make a vector of things. And you can, I'm not sure how far that goes. I mean, it doesn't go very far before I can't keep it in my head anymore, but I can do 2 dimensions. 3 dimensions starts to get quite difficult, but I can do 2 dimensions. So this is, you can think about this as being sort of rows with columns or columns with rows, however you like it, a vector of vectors. No. So that's a good question. Can a vector of vectors hold, can each row, for example, be a different kind of thing? And the answer is no. At the end of the day, there has to be one kind of data type that's in there. You can also, so Isnam asks, are vectors like arrays? Yes. Vectors are like arrays. The main difference between a vector and an array is that an array is of fixed size, and vectors can dynamically grow and shrink. So after you've created an array, if you created it to be of size 10, it will only ever be size 10. It can't be less, it can't be more. A vector, though, you can actually start it. These are all size 0 vectors. And then you can append things to them, and they will grow over time. And you can actually go back later and erase things from them, and they will shrink over time. So vectors are very dynamic in terms of their size. Arrays are of a fixed size. But in terms of their behaviors, they're the same. So we loop vectors and arrays exactly the same way. We associate a specific kind of data with an array, just like we do with a vector. There is a built-in array type now. I don't know if we're going to use it or not. So anyway, hopefully that answered that question. Okay, so vectors can be of a variety of different types, but we're going to worry about this string one for starters. I think, let's see if this is true. Yes, no, maybe, never, unknown. Let's see if that'll compile. Yeah, okay. So you can initialize vectors, and then you can go back later and you can say words dot pushback another word. Yes, no, maybe, never, unknown, certainly. Yeah, and then the vector will grow, which is how it's different from an array. Okay, so you can pre-initialize a vector with data, and then you can go back later and you can add stuff to them. So now we need to start thinking soon of composition, because I have a vector of strings. What is that? Well, if I think of each string individually, that's a collection of characters, if I think of characters individually. So now I kind of have 3 layers that I can work with here. I can work with the entire collection of strings. I can loop through the collection and grab single strings. And then I can loop through the single strings and apply character operations on the elements of the single strings. Okay, so we have a vector of string called words. Let's go look at vector. Is that here? It is here. So here's the vector page. Let's go look at its functions. Here's all that allocator and reference stuff. We're not going to worry about that. They do have an assignment operator, so you can overwrite them. Vectors can be overwritten with other vectors. But notice this. They have iterators. And turns out that the magic of the for each loop is because of these iterators behind the scenes. So behind the scenes, that for each loop is actually using these iterators. So strings had them. I'll go show you string again. Here's string. Has the same iterators. So if a for each loop works on a string, it will definitely work on a vector. You just have to remember at what level you are iterating. So if I'm iterating a string, I'm getting characters. If I'm iterating a vector, in our case, I'm getting a string. Notice, by the way, we have some familiar functions here. We have a size function. We don't have a length function, but we do have a size function. We have an empty function to tell us, just like if it were a string, we can see if the collection is empty of contents. We have the at function and the square brackets, which gives us read-write access to individual elements. We have front and back, which give us the first and the last element, just the same as the string did, except for you have to remember what's in the vector versus what's in the string. What's in the string is always characters. What's in the vector is different based on the vector. We have pushback. You can also do that with characters on strings. For a vector, you push back whatever that vector is designed to hold. You can pop back, which I'm pretty sure strings probably do as well. Yep, strings will pop back also, which is remove the last thing, which for a string is a character, which for a vector is whatever it holds. You can insert into a vector just like you can in a string. You can erase from a vector. You can do that with a string. You can clear a vector. You can do that with a string. So you'll notice that there's a lot of common behaviors here. As long as you remember when you're working on a string, what does that mean? That means it's characters. What are you working on when you have a vector depends on the vector. So here are the words. I can push back. So I can say first item is words.front. Last item is words.back. And then we'll say, to get to the chase faster, index 1 is index 2 is so let's see, the front one should be yes. The back one should be certainly because I pushed it back. That's front and back. Index 1 should be the no. Index 2 should be the maybe. And oh, there it goes. So yes, certainly, no, and maybe, just as expected. Same behaviors as the string. I just have to remember when I words front, I get a whole string. When I S3 front, I get just an individual character. So this is just keeping your brain active. There's no big tricks here. It does take some getting used to, but these are two of the easier collections to deal with. We can loop them. Words.size, I++, very familiar. And this time, let's just print them out. So I'll print out the index as well. And I will use the @I. But I will put a comment here for you that I could just as easily have used the square brackets I. Same thing. So there they are. Yes at 0, no at 1, 2 is maybe, 3 never, 4 unknown, 5 certainly. I can, for each loop them, read-only style. Okay, so now I'll ask a question in chat just to see where we're at. I've been kind of motoring along without giving you guys a chance to kick in anything. So for this for each loop, what are the individual elements? What kind of thing am I getting as I iterate over words? Strings. Nice one, Tony. String. So it just takes a moment to stop and study. So words, what is that? That is a vector of string. So if I iterate a vector of string, I'm going to get string. This is a read-only loop, so not much I could do with it, except I could do this. I could take that string and say, let's just get the first character off of it. So I'm actually going to take the string and I'm going to grab the first character by fronting it. I also could have done @0 or square brackets 0. In this context, it seemed to make sense to me to use front, since that's kind of precisely what I want. My REPL is barfing a little bit. Whatever. Oh, shoot. It didn't sync it back. Holy moly, this goes way back in time. Hold on a second. Oh, no, it's okay. It's okay. Anyway, my REPL kind of hiccuped. Okay, so there I'm actually iterating the vector, and then for each string of the vector, I'm actually plucking off the first character of the vector. So that's a read-only loop. Let's do a read-write loop and then decide what we could do with that. So we'll get references so we can overwrite things as we want to. So let's, what do we want to do? Let's make them all be all caps. So we're going to, do I want to do that? Let's just capitalize all of them. So we'll start with that. So we'll loop through and we will say index 0 is the to upper of index 0. So the first letter in all of them will be capitalized. It's a vector. I can't just print it out. But let's use a for each style loop to print out the changes. Okay, so I'm going to use a read-write loop to alter individual characters note by uppercasing. So I'm going to uppercase the first character, and I also could have done this, by the way, which maybe I should do. I could overwrite the front by capitalizing the front, which seems like capitalizing, doesn't it? Uppercase the front and overwrite the front means that you have capitalized the front. But let's see if it works. So there they're all capitalized as the last thing. Okay, so I think I need to stop there and get you some lab tips. So let me make one and get the lab code and try to give you some tips to get started on that. So let's just say 21 lab 7. Okay, so this is video only. I'm not going to post the code here because I do want you to work with this, but I also at least want to give you somewhere to start from. Is this the lab? Yeah. So I'm going to set up the lab real quick, which is putting all these files in my REPL, and then so here's lab 7. I can do this in main. So let me just do all the setup real quick. So there's the unit test. So that's fine. I need a functions.h. I need a functions.cpp, and I need a wordlist.txt, and then let me go get that stuff from the GitHub. Wordlist. Raw. Okay, there's wordlist. Let me get functions.h next. And then functions.cpp last. Oh, not much help there. Okay, so what does this lab want us to do? We can see everything that's required of us in the .h file because our job is to implement all of these functions in the CPP file. So there's a function that will populate a vector of strings with the contents of a file. There is a function that takes a string, uppercases the string, returns the uppercase form of itself. There's a to lower version of that. There are these character counters, count how many digits, count how many punctuations, count how many vowels. And then some composition involved in looping through a vector. And then using these helper functions to count categories of individual characters. So how does all this work? Your code will open this wordlist file. It will populate a vector. Each element, each line of the file is one element of the vector. And then you will have functions that loop your vector and pass your string to the string counting function. So you have this sort of layers. You make a vector of strings. You loop the vector of strings and you pass the strings to string functions. In the string functions, you loop the strings and you call character functions from there. I'll do a couple of examples just to help, but this is online only stuff, so please get the word out that if people want to see some of the hands-on stuff, it's going to be here and not posted. The other samples will be posted. So let's start with the, I'll give you the file thing because we're about to run out of time. So I'm going to ruin all your fun here. Vector of strings, read file. So the way to do this is from the .h file, I'm going to take the header, Control C to copy. I'm going to go into functions.cpp, and I am going to put the implementation. So what does this thing do? Well, it creates a vector, populates it, and returns it. All right, that's all fine and good. How does it populate it? Well, it opens up an input file stream on this file name, checks to make sure it got it open, and then does the same loop that we did last week. So string, next line, while, get line, file, next line, file contents, dot pushback, next line. So I'm not really spoiling much for you because this function doesn't do much. But you want to study it. So here I declare an empty vector for string. Why? Because I'm about to read a file. And I'm going to take each line of the file and make it one of the elements in the vector. So each element of the vector is one line of the file, and I'm just going to read them in as strings. I'm not going to do any parsing because this lab doesn't say anything about parsing. It just says, read a line of the file, put it in a vector. So fine, I have a place to put the contents of the file. I open up a file. The file name is from the parameter. So what file name? I don't know, I don't care. And this is something that you need to get used to. When you're implementing a function, don't worry about anything that you don't have access to in the function. In this function, I don't have access to much. I don't know what file. I don't know what the file's contents look like. I don't know if it's numbers. I don't know if it's got colons in there. I don't know if it has fields in there. I don't know anything. All I know is I've been given a file name and I've been told to read its lines into a vector. Fine. So I open that file. I check to make sure that it got open. Now I did what I did last week, which is I need to set up a string to contain the file's contents as I read it line by line. And then I use the same while loop. So I'm going to get a whole line from the file, store it in next line, and then I'm going to push that onto the back of my vector. So the first line is the first item, and the second line goes behind that, the third line goes behind that. When this while loop finishes, there's no more file to be read. These file contents should be all the lines in the file. That's it. That's all I can do in this function. I don't have much options. So there you go. I don't know where the file is. I don't know what it looks like. I don't know anything about it. I was just told just read all the lines and put them in a vector. So fine. Now I'll show you just one example of doing the composition part. So I will do what's vowels. How about no, vowels we just did an example of. Let's do digits. Notice, by the way, where are the digits coming from? I don't know. I don't care. They're coming from this string input. That's all I know. What does the string look like? I don't know. Does it have digits in it? I don't know. So this you just kind of need to work on being comfortable with. I have this function. I know what I'm supposed to do because it tells me what I'm supposed to do. What I'm supposed to do is count all the digits in the input. Well, here's the input. So I need to write an algorithm that counts the digits in it. Well, I know how to do that. So I better have a count. Better make it start at 0 since these things don't automatically zero themselves out in C++. I'm going to use the for each loop style because that's the one that seems easiest to me. If I'm counting the digits in input, then it's input that I'm for eaching, which is a string, which means I'm getting chars. So how do I know? Oops, something happened. I don't know what that's from. How do I know that a read only works? Because I don't have to change anything. I don't have to overwrite anything. I don't have to alter anything. I'm just looking and counting. So if is digit that character, then count plus plus. That's it. Where did the string come from? I don't know. Where does the count go? I don't know. None of that stuff matters. So some of you may already be where you're comfortable with that, but that's, again, kind of the challenge for you is to get to the point where you can be given an empty function and told what it's supposed to do, what work it's supposed to perform, and not worry yourself with any of the other stuff that you can't control. I can't control what the input is or where it comes from if I'm working solely from the perspective of this function. What is it? Where did it come from? I don't know. I don't care. That has nothing to do with my ability to loop through it and count the digits inside. Has no effect on that. So now let's go up one more level from there. If we look down here at the vector section, there is a all digits function. So let's take all digits and implement that. So what does it say it's supposed to do? Compute the total number of digits in all strings in a vector. Okay, so there's two layers of looping here, right? I'm going to do it wrong first, and then I'll ask you guys, think about what it is that I'm doing that I don't have to do necessarily. So I'm supposed to count all the digits in all of the strings in this vector. So now I have a collection of strings, which I know have individual characters inside of them. So let's give ourselves a count. And then do the work inside. So I'm going to for each the vector, knowing that I'm getting strings out of it. I think I haven't been consistent about that space right there. For each string s that I pull from the vector v, I'm using a read only. That should be my default unless I discover that what I want to do is not possible with a read only for each loop. So I'm supposed to count the digits. Well, I know that, and heads up, I'm about to do something silly. Well, I already know how to do that, so I'm saying it string count 0 for each character in the string s if is digit this character, then the string count can be incremented. And then when I'm done with that loop, I can increment the overall count with the count of the digits from that individual string. So I count the digits in the individual string, and then I add that to the overall count, the summary count. So last question before we close out for the day. We've been sitting here for a while. What did I do that was a complete waste of my time? Trickier one. I did something in here that was a waste of my time because I'd already done it once. Maybe people aren't seeing it. So another way to ask that is, have we seen this code before? This if is digit stuff. And if we did, where did we see it? There's a function for that. So Tony's right. This code right here, where I count the digits from this vector level, well, I'd already written that code in this other function. So why not figure out if I can compose the solution by these two functions working together? So all of this code is basically the string count. In fact, I'll just eliminate the middlemen and steps. The string count is actually this other function, digits, given a string, s, and now I don't have to reinvent the wheel. So I don't have to count the digits in each individual string because I already have a function that does that. So I will compose a solution to this problem by using the other function. And if I want to, I can just save myself even more trouble and just cut straight to the chase. So that's it. And you should be looking for this everywhere in this program. This program is designed to work this way. It's unit tested, so it's going to have to pass all these tests ultimately, which makes it a little bit more challenging. Well, let me show you. Man, I'm starting to run. I'm kind of way over time. So what if I want to not use the unit tests? And then real quick through this. What if I need to do some experiments and this unit test is getting in my darn way? Well, I'm just going to do this. I'm just going to comment this whole thing out, basically. All the test cases. And I'm going to comment out. So I'm going to comment out all the unit testing stuff. And I'm just going to write my own main just to test the parts that I want. So I could, for example, say, I'm going to need some includes for this. So I can disable the unit test stuff and just test my individual functions like this. So see out digits, hello, 1, 2, 3. That has 3 digits in it. So when I run that, it should tell me it's got 3 digits in it. So that was correct. I can do a vector of strings. Just call it strings. And then I can do a cout all digits of this vector, which should be 1, 2, 3, 4, 5, 6, 7, 8 of them. And so on. So the point here is that you can disable the unit test, write your own little program to test the individual pieces if you want. And then when you're done, take all that stuff that you built your little temp test with and re-enable the unit test, which is going to crash and burn spectacularly right now. So there's a lot going on here in the last 15 to 20 minutes of class. So you can disable the unit test. Make sure you re-enable the unit test. Or you can make a separate file, however you want. But anyway, you don't have to limit yourself to the unit test. You can write a program off to the side and test these things out for yourself. And see if the functions kind of do what, given some predictable input, if they perform correctly. Okay, I'm not uploading any of the lab stuff, so hopefully the lecture video is enough to get you going on those things. So Canvas Inbox, office hours, Piazza as always. Thanks you guys for sticking around, for those of you who could, and let me run over. So I'm going to stop here. I hope I have armed you well for the lab this week. Please look at Project 2. After this week, you already have some of the skills you actually before this week, you already had some of the skills you need. So Have a great week, and I will get your project grades to you before I go to bed tonight. Hopefully just the afternoon will stay open for me and I can just bang those out. And otherwise, I will see you on Monday, late morning next week. So everybody take care.